All right, so today we will talk about Newton's second law based on what we did in this section so far. So the lab that we did on Monday, right? The little carts and the weights. As you bend this ruler, what happens to the car with the weight?
It moves.
How did the weight change what happened when you were playing with the car? Why is it not moving? I'm bending the ruler. Why is the cart not moving?
It's too heavy.
It's too heavy. So what happens if I remove the weight?
It'll go flying.
Oh, man. You hate to see it. You hate to see it. Boyd, I thought you were going to catch it. So why did that happen? Same amount of force, right? Same bend on the ruler. But what happened when the car got a lot lighter? It moved. Away it went. So Newton's second law, this will be a core formula going forward in physics. Force equals mass times acceleration. And what Newton's law basically states is, for any given force on any given mass, the acceleration is related to that. And in this case, the acceleration is inversely proportional to the mass. And we're going to see that next. So if you have some amount of force, let's just say you have a force of 36 newtons. And you have a force of 6 kilograms. Based on this equation, just some quick and simple math, what will the acceleration be on this mass? 6, right? I'm not a math whiz, but I can do 6 times 6 equals 36. Right? So what happens when we have the same force and we make the mass a lot bigger? What happens to the acceleration now? It decreases. What's our number here? What is the acceleration here?
3 meters per second.
Squared, come on. So now does this make sense intuitively? And again, this is where this comes into just being physics, right? If I push something with some force, a 6 kilogram thing, that thing is going to accelerate. If I use the same amount of force and I push something twice as heavy, right, with twice as much mass, is it going to accelerate the same amount? Same force, much bigger mass. Is the acceleration going to be the same? No, why not? This just makes sense intuitively. It's heavier. If I apply the same force to a bowling ball and a basketball, right, which one is going to accelerate faster? The basketball, for sure. It has less mass. Right? This works the other way as well. What happens if I use the same force on something really light? Now what's the acceleration going to be? 12 meters per second squared, right? It's going to get really big. Again, this is all just in service of telling you mathematically what you already know intuitively. You already know, yeah, if I apply the same amount of force to something with less mass or more mass, the amount of acceleration that thing experiences is going to make some kind of sense. The bigger it is, the slower I can accelerate it. The larger it is, the slower or lower the acceleration will be. So there's a worksheet just to practice some F equals ma problems. I'm going to hand that out at the end of the hour after this. But the next thing we want to go into are vectors and scalars. Now, these are two mathy kind of things. But we're going to use them a lot in the world of physics. So vectors in physics are something that have a magnitude and a direction. A scalar quantity only has magnitude. So in this case, speed and velocity are the two examples here. Which one is which? I'm talking about speed and I'm talking about velocity. Which one is the scalar and which one is the vector?
Speed is scalars.
Speed is scalar. Why?
Because it's without the direction.
It's without direction. That's really by definition, is it not? The definition of velocity, if we think back to velocity, was just speed plus you add direction. Distance and displacement are the same pairing. Where distance is just how far did you go? Oh, I went 10 meters. Displacement is the same thing, but now you're talking about adding a direction to it. What about something like mass? Is mass a vector or a scalar? We just had in the previous problem, 6 kilograms. Is that a scalar or a vector quantity? Scalar, why? I agree, but why? Does mass have a direction? Yes, it's 6 kilograms north. That doesn't make any kind of sense, right? Scalar quantities are just some kind of number. It can be a large or a small number, but that's it. It doesn't have direction. So that's going to come into play when we talk about velocities, we talk about accelerations, we talk about forces, momentum, all the rest of these things that we're going to discuss. We're going to have to discuss not just a number, but also some kind of direction. So with that, we need to learn. You guys are not going to believe it. But there's math with vectors. And we're going to start with an easy math problem. We're going to practice adding vectors. So in this case, we're just going to use displacements, right? Distance and direction. If I walk 60 meters east and then 40 meters west, what is my total displacement? What's that? 20 meters. Not quite. Nope. That's your total distance, yes. You went 60, then 40. So your total amount of steps would be 100. That would be a scalar quantity. To make the answer a vector quantity, what would your answer be? No? Total displacement, yes, meters and direction. So what's our direction?
East.
20 east or 20 west? Which is it?
It's 20 meters east.
Good. So the way we do this, you can do this just with the simple math and use plus and minus, right? But we walk 60 meters east. And then we turn around and walk 40 meters back the other way from where we started to where we ended up is what displacement? 20 meters, and then where did we end up, east or west? Technically true. We're going to talk about how you can have multiple answers for the same thing. We're going to do that in a minute. All right, so this was the easy one. Let's make this a little bit more interesting. If I take this journey instead, what is my total displacement? And again, displacement here, each of these movements is a displacement. So we have a distance and a direction. And then my overall answer will basically be where I end up. If I start by walking 12 meters north, and then I walk 8 meters east, where will I end up? How can I set up this problem? My advice would be to start here, not here. 12 meters north, then 8 meters east. Where do I end up, and how would you describe that displacement? What do you think? Yeah, good. So where did I end up? Put your pencil where you ended up. Okay, so how do I find out where that point is? I think you're right. Okay, so how do I figure out what that point is, though?
Oh wait, no, it's like a point. It's like an order.
Would it just be like? I don't know how to explain it. Would it be like this?
So I would draw that first. Draw the coordinate first. Yes, yes. But then how do I describe this spot with a vector? Did you finally get it? Here, let me hang on to that for you. All right, so if we go 12 meters north, and then we go 8 meters to the east, most of you got this far. But now what? Well, we ended up here, right? This was our start. And this is our end. So now how can we begin to describe this resulting vector? This will be from what we did last week. So if this is our scenario, the triangle that I walked, what did I say it was? 12 north?
12 north,
8 east. So now I have 8 east, 12 north. So now I'm just solving a triangle, just like what we did last week, correct? I went some amount in one direction, I took a right turn, went some other amount. Now I can just solve for, how can I get this number? How do I solve for x? I don't have the angle yet, though. Pythagorean theorem. Good. So that'll give me, how do I do that? A squared plus b squared equals c squared. So x will equal square root of 8 squared plus 12 squared. Everybody with me so far on the Pythagorean theorem? That should be some basic geometry stuff. X equals, what'd you get, Boyd? 14 point something? 14.4 meters. Okay, so that helps. 14.4 meters to make it a displacement. What'd you say? Northeast. Now, I agree with that. However, I'm going to say here in physics, we need to be a little bit more precise than just to say northeast. How could I be more precise on where exactly I went? What the direction really is? What's that?
He said it.
What?
I said
more northern.
More northern-ish. Still not very precise. If there's an ish in your answer, I feel like we can do better. How can we do better with what we learned last week? What if we were to solve for this angle? Oh, I know. All of a sudden this feels like trig again, doesn't it? Oh, I thought we were done with that, Clymer. We did all that trig last week. Can we be done? No. So how can we solve for this angle? Tan, okay. Tan theta opposite over adjacent. Tan theta equals opposite was 8 over 12. Did you figure it out? That's great, but in your calculator. How many? 33.4. Now, here's the worst news. Now we have a good answer, but now how do we describe it? 33.4 degrees northeast? Would that work? How do we accurately describe what we're doing here? Remember, this was north, this was east. All right, so our answer needs to look something like this. 14.4 meters, 33.4 degrees. How do we define this 33.4 degrees? Using north and east and using our coordinate system in this case. Not just northeast. We have to be a little bit more precise. Well, this is going to probably... Why did I put east of north in there?
Because you're east of north. You're on the east side.
That makes
Thank
sense.
you. Yeah, because now you know where you're drawing your angle from. Right? Think of the other angle here. There's another angle in this problem that we didn't worry about because we don't care. There's this angle here. This angle, if we were to measure this angle, would be north of east, I guess. Again, precision. We need to be precise in how we're describing what these vectors actually are. So in this case, this 33.4 that we solved for is toward the east from the north direction. Guys, you're going to want to pay attention to this. You're going to want to lock in here for just a moment, because this is critical on how you describe this particular vector for this assignment. So if I found this angle, which is fine based on the information I got, I have to decide what angle that is, where exactly that is, so that if I were to describe this and you had to come over here and draw this vector somewhere in this northeast area, you're going to know where it is. And the way to do that is describe, well, this angle is 33.4 degrees east of north. So if north is here, right, we pulled off of this angle 33.4 degrees. So we're east of the north line, east of north. So let's try another one. Where do we have another one? Down. Here we go. In your notes, draw this and find the resultant vector for this displacement. My advice would be to start with a little coordinate system, just a little bitty plus sign. Plot this out, get your triangle, and then solve out your triangle. Do that all first. And now again, because this is physics, I'm using north, east, west, and south versus in a math class you'd be using quadrant 1, 2, 3, and 4, or 0 through 90 degrees, or whatever. Plot out what this would look like and what my resulting vector will be. East, then north. Okay. Good. Okay. So kind of draw, it doesn't have to be this big, but just draw another like quick one of those. So you can plot out exactly what that's going to look like. Yep, good. Now solve out that triangle. I would redraw, now that you know where it is, I would redraw that a little bit bigger so you can kind of put some numbers in there. Yeah, that's right. So how'd you do it? Just tan the whole way, and then what'd you do for the 8.3? Just a squared, b squared, c squared? Because you can also use like sine, cosine once you get the angle. Too much work. It's fair. Good. All right, here we go. So let's look at our journey. 7 meters east. We'll call that 7 meters east. And then 4.5 meters north to get to this spot. Draw my resultant angle. And now that I have my triangle, I can kind of redraw it bigger. So I went 7 meters here. 4.5 meters here, trying to find this and trying to find this. So Pythagorean theorem, what do we get for x? 8.3 meters. Quickly, because we're doing right triangles here, and I know we're doing a lot of math, remember, the hypotenuse has to be the biggest number in a triangle. So if you're ever solving these and you get to this particular place and you get a number for x and that number is 5.2, could 5.2 possibly be the right number? No. Right? It's got to be the biggest number. So 8.3 meters looks realistic. What about theta? What do we get for our angle? 32.8 degrees. So how would we describe this resultant vector? How would we describe this? Where did our angle, in this case, where did our angle come from? Northeast again, but how do we describe it this time? 32.8 degrees north of east. Does everybody see how we got to this place? All right, let's make it really hard. Tell me the two-step journey to get to this destination vector. So I walked south and I walked east, just like the before questions, but instead of figuring out what my ending displacement was, I'm giving you the ending displacement. You need to tell me what steps led there. And you don't get to walk diagonally. That's cheating. You can only walk south or east in this case. How do we get to this resultant vector? Hint, start in the same place. Start with a little bitty coordinate system. Draw where you ended up, and then find what pieces led you to that place. How far south and how far east? like Jeopardy. Here's the answer. You tell me the question that got us here. So 17 degrees south of east. So think about where the 17 is. Think about how you drew this triangle. And think about what we're trying to get to. Just YOLO, no triangle? Oh, I see it, I see it. This little bitty thing here, okay, okay.
Yeah.
17 is X. Where's your notebook? Bruh. Yeah? And then where do you put the 13.7? Okay, good, yep. South of east. South of east. Why'd you go backwards?
That one started at east and then that one ended.
But I'm saying if you started here and went back this way, this would be west.
Okay, we'll just flip it around then.
Of course.
Did I get the right answer?
I don't know. I just work here. How would I know what the right answer is? I got to figure it out the same as you. I just chose to go east instead of west. All right, so let's see if we can make some sense of this. Not that. So I'm going in some direction southeast this time, so that's a little different. But again, I'm going to pull this angle, this 17 degrees, south of the east line, right? So it's going to be slanted this way. Oh, boy. So here would be my resulting vector. And I know what the angle is. And what else do I know from the problem? I know the overall magnitude of this vector, right? So 13.7 meters. How do we break that into its pieces? Okay, good. So we're looking for, let's just call it x and y. So to find y, we're going to use what for y will be sine? Sine theta equals opposite over hypotenuse. Sine of 17. What's y equal?
4 meters.
And then x, we'll use cosine?
Yeah.
Cosine 17 equals adjacent, which is x, over 13.7. And what does x equal? 13.1. So this is 4 meters. This is 13.1 meters. So now how would I describe this motion to make it look like the problem before? I would say I went 13.1 meters east, then 4 meters south. Did anybody do it the opposite way? Does it matter that you went east then south? Would that make a difference on where you ended up? No. Versus going south first and then east. Would that make any difference, do you think?
Yes. I mean, it'd be like east of south instead of south of east.
No? Think about this. Think about this. This is the brain teaser part of this. Does this make a difference? A or B? To getting to your final answer the same way? No, why not?
Same spot.
You're in the same spot. Let's see if that works. So let's play make-believe that this is our scenario here. If we go east, then we go south. So we go east to here, and then south to here. We end up there. This way, and then we go this way. What if we do the opposite? What if we go south first, and then go the same distance east? We end up at the same exact spot. So when you draw out this resulting vector, in any case, you're going to end up at that same blip. So in this case, both of these answers are exactly the same. Doesn't matter what order you go in to get there, you're getting to the same spot. I went however far east I went, and then I went some amount south. That will not make a difference. Let's practice all of this.